So imagine you are one of the important person in your company sales team. So you have to travel to various locations in order to meet your clients. So in your company, they say like first they ask you to travel and pay the amount, and then at the end of the month you can reimburse. Okay. So now, so whenever you go to visit some client, you will pay them. So you have a list of like where all you went and what is the amount that you paid.
Okay.
Imagine tomorrow that you want to meet a new client to whom you have never met before. Okay. So the client stays in a different location and you have to travel there. Now, since you had data already related to your client, related to all the distances you traveled so far in an Uber and the amount that you paid, you wanted to find out what will be the fare that you pay the driver at the end of the ride tomorrow for the distance you travel. Okay. You know that the total fare that you pay for a ride depends definitely upon distance. Distance is one key factor, right?
Yeah.
You can have other factors, like for example, the type of the vehicle you choose, the time of the day, whether it's a peak hour or a non-peak hour, the city, maybe whether it's a metropolitan or not, etc. There can be multiple factors that impact the fare of the ride, right? But for the sake of simplicity, let us consider that you are considering only the distance you travel and the fare that you are paying the driver at the end of the ride. These are the 2 points that you are considering. Okay. So let us create a data set and let us are you able to see my screen?
Yes.
Okay. So let us create an Excel file. Here you go. This is the distance. And this is the fare. Distance is in kilometers, fare is in rupees. Okay. So let us say that the distance you travel is like 3 kilometers, 5 kilometers, 8 kilometers, 9 kilometers, 11, 12, 13, 15, 17. These are the distances you traveled. Examples, 9 examples, let's say 8. And the fare that you paid at the end of each and every ride is, let's say, 33, 48, 77, 72, let's say, and 84, 125, and 136 rupees, 154 rupees, 170 rupees, 181 rupees, and 203 rupees. These are the fares that you paid to the drivers at the end of each ride. Okay.
Okay.
The idea is, using this data, you should be able to tell that tomorrow, if you're traveling, let's say some 20 kilometers, for example, tomorrow your ride is 21 kilometers. Let's say, what is the fare that you pay the driver at the end of the ride? That's the question. Okay. So if, for example, if you are given this question, what is the approach that you take?
So I'll see per kilometer, what's the fare? Then
How do
I
you
multiply.
Because it might change, right? For example,
Yeah, it'll change from different one. Yeah,
11. Here it is not 11, right? Here it's 9.6. It keeps on changing.
Can I take the average of?
Very good. First step is the average of the distance that you travel, right? Is this. And then you can take the average of the fare also. Okay.
I think you left the last one there.
Did I? Okay.
The distance.
Okay. Yes. Right.
The average.
Yes. So the total is, we traveled so far on an average, the distance traveled is 11 kilometers and the average fare is 120 rupees. So for 1 kilometer, it is approximately 10.86. Okay.
Multiply this into 21.
Yes. So now for 21 kilometers, it is equal to 21 into this. So your approximate fare for the ride is going to be 228 rupees.
Right.
Right. So Now let us take one approach. Okay, this is good. This is definitely it will help us in the right direction, right? But there is one problem here. The problem is, let's say we have so many other important factors, like not only just like, the distance, there can be other factors as well that impact the fare, right? But here we are just considering only this single variable. Do we think like, but before we confirm the 228 is the best prediction, okay, let us do one thing. Let us see that since it says that for every kilometer, the total approximate ride fare is 10.86 rupees, we'll create a new column called predicted fare. Okay.
Okay.
And what we do is for these distances traveled, we already have the fare for a kilometer, right? Let us apply this for all the existing values first and see whether our predictions are close enough to the actual values or not. Okay. Because how do we rely that this 228 is right? Right? It's for future, right? Hello? Hello? Okay, so now we have the distance per kilometer, we know the approximate fare. So for each and every distance that was already traveled, we will calculate the predicted fare. Okay. So that is equal to the 3 into this value, and I am locking this cell so that every cell will be multiplied only with 10.86. Okay. So now these are the distances, the predicted fares for our ride. Okay. So for 33 rupees, it said 32.5, 48 rupees, it said 54, 72 rupees, it said 86. I think this is definitely some considerable difference, right? 84, 97 again, yes. 125, 119, okay. 136, 130, okay. Again, some 13, 14 rupees again difference. And so on. So our predictions are fine, but not like very great. Agreed?
Yeah.
They're like, okay, it's not like the best prediction, but still not too off, but still okay, right? So let us see how we can measure whether our predictions are good or bad. Okay. So before we do that, let me first shift all of these into its concern. Okay. So now we have our distance that we have traveled. We have the actual fares, and by some technique, we have created our predicted fares.
Okay.
Now in this step, let us see whether our predictions are good or bad, or how good or how bad. Let us try to measure them. Okay. So what we do is first, the best way definitely is always to visualize the data so that we know how it is. Okay. For the distance and fare, I am going to insert a graph. Okay. This is how our fare is changing with distance. Where on the x-axis we have the distance traveled, and on y-axis I have the fare. Okay.
Okay.
So now distance fare. Okay. So now here we go. So this is our graph. So we know that the main idea for us is, if in order to make a better prediction, the main idea is we should always know we should definitely know the relationship between our fare and distance. I'll tell you what I mean. For example, let's say that I'm going to add my predicted fare here. Okay. So I make the series as predicted fare, and my x is going to be the distance that I travel, and my y is going to be the predicted fare. Okay.
Okay.
You can see the orange dots. The orange dots are our predicted fare, and our blue dots are our actual fare. Right?
Okay.
They're pretty close enough, fine. But like sometimes they are bad and sometimes they are good. It is that's how it is, right? So let us see how we can really make our predictions more and more reliable. Okay. So in order to do that, let us say, I'm sorry. Okay. Okay, so here what we try to do is so in this case, if you observe or if you see our predicted fare and actual fare, for example, for 3 kilometers, it is 33 is our actual fare, 32.5 is our predicted fare. So it's like almost the same. But there are values for 8 kilometers, 9 kilometers where they are a bit off, right?
Yes.
So and so on. So definitely there is something, but it's not like definitely the best of our predictions, but yes, they're considerably, they're fine. So now, since we have our data, let us say that I'll give you one more slight different example, okay? For the same data, let us say that the fare is, let's say, 30, 50, 80, 90, 110, 120, 130, 150, 170, and 180. If this is the case, then for 21 kilometers, what will be the fare? On?
Yeah.
So if this is the case, if this is our data, then for 21 kilometers, what will be my fare?
The same way we can do it. No?
Think of it.
Okay, so 210.
Why 210?
Because it's proportional.
Exactly. So in this case, we can still do it the same way. For example, if I take the average of all these, what is it equal to? 11.1. If I take an average of all these, 111. If you still do that, it will come to the same, right?
Yeah.
So for per kilometer, it is 10 rupees. So 3 into 10 is 30, 5 into 10 is 50. So 20 to 10, 210. Still that works. It's not like it's wrong. Okay. So,
Yes.
but it is like very evident here in this case. It is the relationship between my fare and distance is fare is equal to 10 times the distance. Right?
Yeah.
That is our relationship. But in this case, the relationship is not very evident. Agreed? So if we calculate it using our average method, we got that the relationship between our distance and fare is, our fare is 10.86 times the distance. But that will not give the exact value because the data sometimes is fluctuating. Sometimes it's increasing, sometimes it's decreasing, right?
Yes.
But the best average is 10.86. So based upon that, we are able to come to this conclusion, right? But basically the main idea is to bring a relationship between our fare and distance.
Yes.
Because if we are able to bring a relationship between our fare and distance, or observe how our fare and distance are related to each other, based upon that, we will be able to find out tomorrow, whenever we get a new distance, we will be able to find out the fare. Agreed?
Yes.
So in this case, if I actually draw a graph, okay, do you see that it is in a straight line?
Yep.
So it's like very easy because our data is just in a straight line. So definitely you can actually see like the equation of this particular straight line. The equation is 10x, right? That's the equation. So it's like the distance between our x and our distance and fare is like very clear here. But if you look at this graph, the distance and fare, okay, do you see that the I'm considering only the blue points, the actual fare. Do you see that? Is it in form of some straight line?
No.
No, the data points sometimes are higher, sometimes are lower, right?
Yes.
So if I even draw a graph between them like this, okay. If I draw a graph also, it's like some polynomial curve will come, right? Some curve like this. Agreed? First, calculating the equation of the curve is very hard because sometimes the data is increasing, sometimes the data is decreasing. Calculating the equation is pretty hard.
Okay.
Second problem, even if I calculate the equation need not be always reliable. I'll tell you why. Because in this case, let's say for 11 kilometers, it is 125 because let's say I'm using an SUV here, okay? And for 17 kilometers, it is 181. I'm using an Indica, the type of the vehicle. So for 21 kilometers, again, if I use an XUV, okay, then the fare can be much higher, right?
Yeah.
But there is nowhere mention about the kind of vehicle. Agree?
Yeah.
So even still, even if you calculate that complex equation and all that stuff, there are some variables that are not accounted into that equation, right?
Yes.
So when that variables come into play, even after doing all this hard work, still our predictions can be unreliable. They can be only reliable on our data that we are training with, only for this. But in real time, that predictions might go for a toss. Do you agree?
Yep.
Because we are not considering the other variables into account. And that is the reason why what we do is we do not try to find the exact equation of this particular curve. Okay. But instead, we try to fit a straight line that approximately goes through the data points like this. That approximately goes through each and every points. Or we try to find an equation in such a way that the distance between the points onto our straight line is minimum. Okay.
Yep.
Before we do that, let us deal with one more aspect. Okay. Let's say in our case, okay, I'm once again onto our graph. I'm adding our predicted fare so far, right? And our X is this, and our Y is this, right? See, even then, this particular orange line, it's actually a straight line only. If you observe very closely, you see that?
Yeah.
All our orange lines is a straight line because the equation of the orange line is Y is equal to 10.86 times X, right? That is the reason it is Y is equal to 10.86 times X. That is the reason why this orange line is also a straight line only. Agreed? So if you like, if I say display equation on chart, you see Y is equal to 10.865 times X. It's just a straight line only, right? So even then, this is a straight line that we had created. So now, but we'll also see in the future whether that is the best fit straight line or not. That is something that we see later, okay? But in this case, we have created like a predicted point and an actual point. Now our aim is to find out how well our predictions are, right? If my prediction is better, it means that the distance between the orange line, orange dot and the blue dot will be close enough to zero.
Close. Yeah.
Right? If my prediction is bad, the distance between them increases. Agreed?
Yes.
So what I try to do is I try to find out the distance between each and every data point. Okay? Between these 2 points, what is the distance? Between these two, 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 and so on. Okay? I try to calculate the distance between all these sets of data points and then calculate the average distance. Okay. If the average distance is close enough to zero, which means all my data points are close enough to each other, right? The predicted and actual fares are close enough to each other. So that is a measure for us to tell whether our predictions are good or bad. Does it make sense to you?
Yes.
So how do you find the distance between these 2 points, for example? What is, do you remember the formula to calculate the distance between 2 points? That's okay.
Physics.
If you don't remember, yeah, that's okay. Long time.
Speed into time.
No, that
is different.
That's different.
Distance, speed by time.
No problem. So actually, generally, okay, imagine that there is a point here. Let's call this as x1, y1. Okay. There is another point here, and let us call x2, y2. Okay.
Yep.
The distance between these 2 points, is given by the formula square root of y2 minus y1 whole square plus
x2 minus x1 whole square.
Very good. It is x2 minus x1 whole square. This is the distance between the 2 points. Okay. Now, in our case, okay, in our case, if you see this point, for example, and this point, can you see that for the orange, the moment I hover my mouse on orange, there will be one small tooltip that appears, series predicted fare 0.8 and all. Down to that, there are some coordinates. Do you see that?
Yes.
8, 86.92. 8 represents our distance.
Hmm.
And 86.2 represents the predicted fare.
Okay.
And what if I put on the blue point? What does it say? 8 is our
8,
distance.
72. 72 is the
The
fare.
fare,
Predicted
actual fare, right? Do you agree?
Yes.
So now, if I want to calculate the distance between these 2 points, I do x2 minus x1 whole square plus y2 minus y1 whole square under square root, right?
Hmm.
But in this case, what is x here?
X is 8.
Exactly. For this, what is x?
8.
The same, because the unit is distance, right? Distance is 8 kilometers. For the same 8 kilometers, we have a predicted fare and we have an actual fare. So x is same, right?
Hmm.
So in our formula, x2 minus x1, they get cancelled out. Because x2 and x1 both are 8 only, right?
Correct. It is 0.
Now, this square and root will get cancelled now. Then what is remaining?
y2 minus y1.
Which is nothing but this point minus this point. The predicted
86.92 minus 72.
72. So that is called as our error. That is our error in terms of prediction. Okay. That is the predicted fare minus actual fare. Agreed? Do you see that sometimes my predicted fare is greater than 0, sometimes my predicted fare is less than 0?
Yeah.
Right? That will definitely give us a problem while we are calculating an average error. Because the positives and negatives tend to cancel out, right? I'll give you one example to better understand that. So I'll tell you the actual value and a predicted value. Okay. Can you calculate the error and tell me, and the average error as well? Shall we try that?
Yeah.
Okay. So let's say the actual value is, let's say, 35. 37, 39, 41, 43, 45. These are the actual values. Predicted value is 37, 35, 40. Again, let's say 40, 44, and 44. These are our predicted values. Okay. What is our error?
35 minus 37.
Generally, we say predicted minus actual. We can tell the other way also. No issues. Okay.
Okay.
And what is my average error?
The total of error divided by.
Yeah, the count of the error. So I'll just do the average formula. What is our average error shows?
0.
But error 0 means there is no difference between predicted and actual, right? But in this case, is there even a single example where our predicted is matching with the actuals?
No.
But still the average error is 0. The reason is because sometimes my error is greater than the actuals and sometimes my error is less than the actuals, right? So the positive and negatives, 2 and minus 2, sum is equal to 0.
Cancelled. Yeah.
Exactly. 1 minus 1, 0. 1 minus 1, 0. So if we add all, it is just 0. The sum is 0, right? So 0 by 6, that is equal to 0. That's the reason our average is 0. Do you understand the importance of this negative sign?
Yes.
Having a negative, not always it will cancel out to 0, but it may not show the real error. Because the negatives will get partially cancelled by the positives. Sometimes the total error might be reduced, right? So that is one problem, because we see error as a measure of our difference between our predicted and actual values. So in order to eliminate this problem, what can we do? What do you think we can do? So what I'm going to do is I'm just going
square it.
Very good. Super. You're on spot. You can either square it or you can calculate an absolute value also. Both of them are okay. Okay. So you can do both of them. So, but in this case, I'm actually trying to square that. Okay. Sorry. Sorry, I had to respond. Okay,
No
so the
problem.
square error is nothing but I am just squaring these values. Also, I can take the absolute value also, but in this case, I'm taking the square, and here you go. Okay, so this is our squared error. Once we get a squared error, then now I can take the average, which is also called mean. So I'm going to call this as my mean squared error. Okay, because then why I got the name is because first I'm calculating error, then I'm squaring the error, then I'm calculating the mean. Mean is nothing but our average. Okay, that is the reason it is called mean squared error. What is my mean squared error now? 79.55. That seems to be big error, in fact.
Yeah.
Right? So now the next step is we should be able to make a prediction in such a way that it is closer to the actual values, right? Which means we should be able to do something such that our mean square error is lesser. Okay.
Yes.
So in this case, we use one famous machine learning algorithm called gradient descent. Okay. What do we do is in order to we use a data science model called linear regression. But let us see what linear regression is and how gradient descent comes into picture and helps us solve this problem to make our predictions much more efficient. Clear? So for that, my idea is in this case, between our, so we have these predicted values and actual values, but for all my by all my actual fare, I want to create a line like this. Okay. I want to create a line like this, such a line which approximately passes through all our data points. Okay. Let's call it as black. Okay. I want to create a straight line in such a way that it closely passes through all my data points, my blue points. Okay. If I'm able to create this straight line, if I'm able to create this particular straight line, then what happens? Sorry. Then what happens is tomorrow, whenever I want to find out for 20 kilometers, for example, if I want to make a predicted distance, I can just increase or extend this line, right? Where does this line doesn't go? Oh, or let me insert. If I insert it. All right. If I create a straight line like this, I can increase it further. Let's say for 20 kilometers, right? So tomorrow for 20 kilometers, I can say that this is my predicted fare. Does it make sense?
Yeah.
Because I can increase my line and I can say for 20 kilometers, what will be the fare? And based upon, I can make a prediction for any unknown data. Clear? So for that, we need to find out the equation of this particular straight line that approximately passes through all my data points. Clear? What is the general equation of a straight line? Hello?
I have no idea.
Your voice is too low.
Hello?
Yes, now it is better. So the general equation of a straight line is given by the formula y is equal to mx plus, right? So here I'm going to use the formula as y is equal to theta naught plus theta 1x. I'll tell you the reason why, but we're going to use the denotation of theta naught, where theta naught is our c, which is called intercept, and theta 1 is our m, which is our slope. Okay. Clear? A slope represents the steepness of a straight line. For example, if this is the straight line, slope represents the angle with which the straight line touches the x-axis. Okay. For example, if you see this straight line and this straight line, this first straight line has a lesser angle, so lesser steepness. The second straight line has more angle, so more steepness. Like it is like the inclination of that particular line onto the x-axis. That is what is called as our slope. Okay. And a straight line, there is another concept called intercept. Intercept tells us where this particular straight line touches our y-axis. Okay. So that is the point. For example, there can be two straight lines with the same slope. They are called parallel lines, right? Because they are touching our x-axis with the same angle, but their intercepts are different. Clear? Similarly, there can be two straight lines with the same intercept and different slope as well. For example, I can say this is one straight line and this is a second straight line.
The point
Right?
of intersection will be same.
Exactly. Both of them are meeting at this same intercept only, but they have different angles with which they are meeting our x-axis, right? So these two straight lines have different slopes, but the same intercept. They can have same slope, but different intercept also, like this. For example, I'm taking this line and I'm taking this line. They're parallel lines, right? So they have the same angle with which they meet the x-axis. So their slope is the same, but their intercept is different because they're meeting the x-axis at two different places, here and here. Make sense?
Yes.
Or for straight lines, there can be completely, they can have a different slope and different intercept also. That is also okay, right? So, but for our data point, there is only that single straight line that best fits through all our data points, right? Do you agree? So
Yes.
for these data points, there will be this straight line, a single straight line. There can be only one straight line that can go through all the data points closely. There cannot be any other data point where the mean squared error is the minimum. Okay. Our idea is to find out the equation of this straight line. Okay.
Yeah.
So this straight line will definitely have some slope and intercept. Y is a point on this straight line. That's okay. X is our distance traveled, which is already provided, right? So to create this equation, we just need the slope and intercept of this straight line.
Okay.
So far, any questions you have?
No.
Why we are trying to fit a straight line? Anything? What is a straight line? Any questions anywhere?
No.
Sure, clear?
Yeah.
Very good. So now, so this is our distance and this is our fare. So let me copy it separately into a separate sheet while we are doing this. So in order to calculate the equation of that particular straight line that best passes through all our data points, I'm going to call a random slope and a random intercept. Okay. I'm going to call a random slope and a random intercept. So can you tell me some random values? Your wish.
6 and 20 something.
Okay. So let's say intercept is 6, slope is equal to 20. Okay. Clear? So this is our intercept and this is our slope. So now shall we find the predicted fare? Is equal to theta naught plus theta 1 into x, right? So now I am going to log this formula. Okay. Now you see the predicted fare and the actual fare. Is my predictions close or not close?
Not close.
They're bad, right?
Yeah.
That's okay. So now we are going to first calculate my prediction minus actuals, right? Prediction minus actuals. This is our error. Do you agree? And what is the next step once we calculate error?
Square the error.
Very good. So I'm going to square the error. I'm going to say h of x minus y whole square. Right? That is equal to this. So, okay. And then what is the next step? Once we calculate the squared error?
Then
mean squared error. That is nothing but
average of.
Okay, what is our mean squared error now? 13,082. That's okay. Because we just took random values, right? So it's completely understandable. Okay. But now tell me, can I mathematically write the formula for mean squared error? Let us see what it is. So if I take my mean squared error, we represent mean squared error by a symbol called J. Okay.
Okay.
So first we calculate error, which is h of x minus y, right? Then we are squaring it. Agreed? Then we are doing the sum for every example, right? Sigma is equal to 1 to m. Sigma represents summation. So from the first example till m examples, we are adding all the h of x minus y whole squares and then dividing it by m, which is the count. Is this the formula for mean squared error? Clear?
Yeah.
Any questions?
No.
No. So, but then h of x, what is the value of h of x equal to? Theta naught plus theta 1 into x. That is our formula for our prediction, right? So now, since we calculated j, what are the values that j depend upon? What is m, for example? M represents our number of training examples. Okay. So how many examples do we have here?
11.
10.
10. 10.
10. So m is equal to 10. Okay. This m represents the number of training examples. Sigma anyways represents summation. So let us leave it. And then h of x. In that, what is x?
Distance.
Distance. So this is the distance that you already traveled in your Uber, right? Already that is done, that you have already traveled. So do you think you can change that?
Pardon?
Do you think you can change that?
No.
We cannot, because that's a constant. That is the reason. It is something that has already happened, right? So x is a constant. So nowhere it can change our value of j because its value is just the same. What is y? Y is nothing but our fare, our output.
Fare.
Agreed?
Yeah.
If I give h of x minus y, I'm doing this minus this, right? Bit. Y is our fare, the amount that I'm paying to the cab driver. Can that be changed?
Yeah.
No, because these are the distances that you already traveled, and for these distance, these are the fare that you have already paid.
Already paid. Okay, then
yes,
we can't.
You already paid for this. Our idea is tomorrow you go for 21 kilometers. What will be the fare?
Okay.
But these you have already traveled and you paid, right? So you cannot like change them. So y is also a constant. Okay. So only values that are variables here that can be changed are theta naught and theta 1. Because those are two values that you randomly selected. Agreed?
Yeah.
So in order to change the value of j, you should change only two values, theta naught and theta 1.
Okay.
Agreed? So now what we want to do is, whenever there is a change in theta naught, how much does j change? And whenever there is a change in theta 1, how much does j change? That is what we want to find out.
Okay.
So how do you find that? Which branch of maths helps you find out? No idea?
Regression.
No. The branch of maths that deals with is called saw that? It's a differentiation. Remember in our childhood we did dy by dx?
Yeah.
All that stuff?
Yeah.
That comes handy here. Okay.
By this.
Yes. But actually the problem, you know what actually is, we don't really understand the practical.
1 second. 1 second. I'll just take a call. Hello.
So now you remember the main problem is at that time though we understood and we did a lot of quite extensive differentiation, we may not really know the practical use of differentiation.
Yeah.
Like why we are doing it, right? So and that was maybe one of the reason why we lost interest in that kind of stuff. But actually you can use differentiation practically for solving many of the things in real world also. Okay.
Okay.
Just one small example. Okay. So in order to find out the impact of theta naught on j, we need to calculate the partial derivative of j with respect to theta naught. Okay. And also the partial derivative of j with respect to theta 1. Clear?
Okay.
Maybe in our another class, we'll go into the math behind how dou j by dou theta naught is equal to what and dou j by dou theta 1 is equal to how much. Okay. I'll explain the class maybe in our later class because I don't want to make it too mathematical only in the very first class. Okay.
Okay.
I'll just give you the direct formulas for it at least at this point. Okay. So dou j by dou theta naught is nothing but it is an average, okay, of error, which is h of x minus y. That's all.
Hmm.
If you modify, if you calculate these derivatives, ultimately you will come up with this equation. And dou j by dou theta 1 is nothing but an average of error into x. Okay.
Hmm.
So just let us plug in the equation values here. Okay. We got our this is our mean squared error, right? 13,082, right?
Hmm.
So now I'm going to calculate dou j by dou theta naught. Sorry. Dou j by dou theta naught and dou j by dou theta 1. These are the values that I want to calculate. Okay.
Hmm.
And dou j by dou theta naught is equal to average of h of x minus y, right?
Hmm.
And dou j by dou theta 1 is average of h of x minus y into x. Agreed?
Hmm.
And that is equal to h of x minus y into x, right? So
Hmm.
first we calculate h of x minus y into x, and then the average is calculated here. Agreed?
Yeah.
Oh, very good. So since we calculated h of x minus y and h of x minus y into x, we got dou j by dou theta naught and dou j by dou theta 1 as well. Okay. The last step in our formula, okay, today is we consider one small value as our learning rate. Okay.
Hmm.
This learning rate is generally called as the speed or the rate at which our machine learns things. Okay. But we'll speak about it later in our subsequent classes. But at this point of time, think of it as a very small number, integer. Okay.
Hmm.
So now there is a formula for our gradient descent algorithm with which our machine learns. Okay. It is repeat until convergence theta naught is equal to theta naught minus alpha into dou j by dou theta naught. Okay. And theta 1 is equal to theta 1 minus alpha into dou j by dou theta 1. Clear?
Hmm.
So this is nothing but our assignment operator in maths. Okay, very simple. You remember what is an assignment operator?
Hmm.
First, right hand side will be calculated and it will be allocated to left hand side, right?
Hmm.
So this is our assignment operator in maths. So first we'll calculate this and then put this value into theta naught. Similarly, we calculate this and put it into theta. Clear?
Yeah.
We already know what is theta naught. We already know what is alpha. Alpha is our learning rate. And we also calculated this dou j by dou theta naught, right?
Hmm.
So let us put it here. I'm going to call updated theta naught and updated theta 1. Updated theta naught is equal to actual theta naught minus alpha into dou j by dou theta naught. And theta 1 is updated theta 1 is equal to theta 1 minus alpha into dou j by dou theta.
Dou j by dou theta 1.
And the formula also says do not stop only once, but now once we calculate these values, you have to substitute those values into this, right?
Hmm.
So I'm going to copy these values and paste them. Okay. Do you see our mean squared error has reduced from 13,000 to 2,838?
Yes.
Right? But again, the formula says repeat this process again and again, not just only once. Okay.
Okay. Hmm.
So what is the original value that we took? Is it 7 and 20? Is that
6 and 28.
okay? So this is our original values, right?
Hmm.
Okay. So now we have to do this again and again. So for that, what I'm going to do is I'm going to record a macro. Okay.
Hmm.
I'm going to give that option as Q, control Q. So I'm going to copy these values. Okay. Pasting special here. Okay. I'm stopping the recording.
Hmm.
Clear? Now I'm going to say I'm going to say, once this button is clicked, I'm going to copy this formula that we have recorded as a macro. Okay. I'm going to name it as distance fair, and I'm going to make it as a macro enabled workbook. Clear? Now I'm going to do one last thing. Now this particular button, I'm going to call it as train 1000 times. Okay. I renamed this button to call it as train 1000 times. So this becomes 6, this becomes 20. Do you see I wrote a loop condition there? If you go back to our formula, I wrote from 1 till 1000. Okay. From 1 till 1000, loop this. So what does this do? It actually copies the values in our updated theta naught and theta 1 and pastes them back to the original theta naught theta 1, right? So I told repeat it 1000 times. So what does happen once we repeat it 1000 times? Shall we observe? Yeah. So I click on this. 13,082. You see how it is transformed. You can see our mean squared error reducing. 1000 times it's done. Okay. Actually, I mean, since the computational power is faster, even 1000 times it happened just like a whisk. Okay.
Yeah.
I'm training another 1000 times. Okay. Done. Another 1000 times. 2000 times it is trained. Shall we train another 2000 times? So let us do one thing. So
but theta naught has already gone into minus now.
Yeah, that's okay. Theta naught is just an intercept. It can be a negative intercept as well, right? What we want is our mean squared error to be closer to 0. That's all. Okay. So I'm telling here, I wrote it as train 3000 times now. Okay. So this will train it 3000 times. Even I'm going to call this as okay. Anyways, it'll happen 3000 times now. Okay. Now I've clicked it, so that training is happening on and on and on for 3000 times. The most important thing you should really check is our dow j by dow theta naught and dow j by dow theta 1. Okay. Because they tell you whenever there is a change in theta naught, how much does our mean squared error change? That's what they represent. Okay. When they become closer and closer to 0, it means that any change in theta naught or theta 1 is not really much impacting our thetas. Okay. So that is more important. Let's say another 3000 times. Okay. Sorry. Another 3000 times. I'm doing this. Okay. Okay. So it's like another 3000 times. Okay. You can see dow j by dow theta 1 that become very, very, very small value. Okay. Even dow j by dow theta naught is also becoming a very, very small value. So what is happening when it becomes a small value? This value becomes very small, close enough to 0. Further multiplying with alpha, which is 0.01. So still it becomes a value close enough to 0.
Yeah.
So when we remove a value approximately equal to 0 from theta naught, the result is also again theta naught only.
Yeah.
It doesn't change much. So even if you train so many times also, our theta naught and theta 1 will not change much.
Okay.
That is what it means. So you can stop your training here. Okay. What is the mean squared error you got now?
61.98,
right? What is the mean squared error we got initially? With our average method?
79.
79.55. But now using this method, our mean squared error is still lesser.
Yeah.
Which means our predictions are more reliable than the earlier method. Do you agree?
Yeah. Okay.
So now we'll see. Sorry. Now, okay, for 21 kilometers, the fare is theta naught plus theta 1 into x, right? It is 237 rupees. That is our approximated fare. Okay.
Okay.
But what did we get for 23 here? It is 21. That is equal to 21 into 10.865, right? It's 228 rupees is our price. It's showing, right?
Yeah.
In our average model, it is showing 228, but our model is predicting that it is 237 still.
237.
So based upon this data, for 21 kilometers you travel, 228 rupees is not sufficient. It is 237 rupees. Still it has error. It doesn't mean that it is perfect. Still we have error. But this is the best we can predict using a straight line. Okay.
Okay.
Is this clear?
Yes.
So do you have any doubts on the process that we have used in order to calculate?
No.
So finally, if you go back to our graph, okay. Microsoft will always create a trend line, okay. There is also something called display equation on chart. If I do that, okay, Microsoft will give you that particular equation of that best fit straight line. What is that slope equal to? 11.761 something. If you go back to our formula, L1.76. And what is our intercept equal to? Minus 9.942. Minus 9.942. You see that? So if you give this to an Excel and you say, click on display equation on chart, it does that for you automatically. See? Select the data points and click on this, it will give you this. But how is Excel calculating these? We are able to do that part here. Is that clear?
Yes.
By taking some random value, we used partial derivatives to get the best fit value. Okay?
Yep.
And this is the best prediction that our system can do based upon the relationship between distance and fare. Since it is not, we are not trying to capture the exact relationship between fare and distance. We are trying to make an approximation. Okay. So these values are generalized, which means our predictions will be more better than our, like instead of finding the exact equation of our distance fare curve. Clear? Any questions on anything that we have discussed so far?
No, I'm just.
Does it appear clear or confusing or too math or?
No, not too much. Yeah.
It's okay?
Yeah.
Okay then. So this is nothing but this process of fitting a straight line onto our observed data in order to make a prediction is actually called as linear regression. Okay. The process of fitting a straight line onto observed data. So this is our observed data, right? So this is our data. Right? The linear regression is nothing but it's the process of fitting a straight line like this onto our data. This is what we do in linear regression. We find the equation of this particular straight line that better pass through all the data points. Okay. And how do we use that? We extend this line further. So tomorrow, whenever there is a new data point, let's say like for example, 20, we'll see the fare on this straight line. That will give us our predicted fare. Any questions on this?